Okay, so we have seen in the first hour, we have seen basic concept and definitions of for game theory with application to motion planning, and we've seen a couple or three classes of games which were interesting for different and overlapping reasons. They were easy to analyze. They come with some properties, for example, the existence of a deterministic Nash equilibrium, or the convergence of iterative best response algorithm. And they also come with their own methods, computational methods for their solution. Okay, what we're going to cover now, it's an extension of games to what are called multi-stage games. And we're going to see in a second what the multi-stage games are. We're going to touch a couple, 5 points. We're going to look how to represent them in the extensive form, a subclass of feedback games, what is backward induction in the solution of these games, and then move to loop models and dynamic games, where you can talk about closed loop and open loop and Nash equilibrium. And that's quite some material that will be useful if you plan to use game theory for motion planning. Okay, so first of all, what are multi-stage games? Well, what we've seen until now was a game or examples of games where different players only had to make the decision at the same time and see the outcome. Usually that's not the case if there's a complicated decision problem. And as you can see here in this very pictorial representation on the left, agents interact, here it seems that player 1 and player 2 are interacting first, then 2 and 3. The interaction is happening in multiple stages. While driving, vehicles observe what the others are doing. The decisions are sequential, like you observe what the other one is doing, and then based on that, you decide what to do. Even the number of stages may be longer or shorter, like how long is the game, how long does it last? It depends on how much you interact with others. Plus other things that we're not going to cover too much today, to be honest, like partial information availability of memory constraint players. Like you're an autonomous vehicle, you sure remember what you've just done in your maneuver, but you might not keep track of all the maneuvers you've been doing in the last 10 days, right, or something. So these kind of games are what are called multi-stage games instead of single-stage games. Now, the representation with a matrix or with just a cost function is a little bit falls a little bit short for these games. The typical representation is what is called the extensive form, or a tree representation. So it's a tree where the game evolves, or happens from the root of the tree, which is up here, to the leaves at the bottom and here. Okay. Now each node of the tree is a player's turn to take a decision. So in a two-player game, which is the example I'm using for now, here first player 1 has to take a decision, then player 2 has to take a decision, then player 1 again, and then player 2 again. Okay, so it's 2 decisions each in this case. Links, not surprisingly, corresponds to action. So player 1 decision was between north and south. Player 2 decision is between east and west. And then it's player 1 turn again to decide between up and down, and player 2 decision between left or right. Now, of course, when the game ends, when you get to a leaf of this tree, what you get is the outcome of the game. And here we just attach a label to each of these outcome nodes, and the label tells what's the outcome for player 1 and for player 2, or multiple players if you had more than 2. Now, a tricky part, which is not so obvious, is the introduction of information sets. So information sets are sets that we draw on top of the tree, which contain nodes of the same player, and they represent the ambiguity in the player's knowledge. So for example, player 2 here doesn't know if he's in this node or if he's in this node. He knows it's his turn to play because we are in this information set, and that's knowledge for available knowledge player 2. But player 2 doesn't know whether player 1 has played north or south before. Okay. In some other cases, like in this case, the information set is a singleton, so player 1 in this case knows that player 2 has played east before. Okay. And you have, of course, all possible variability or possible variations are available to you. Now, if you agree on this terminology, then the definitions that we have seen before can be naturally extended. A pure strategy is going to be now not an action, but a map from information sets to action. So a pure strategy for player one is that it's going to play UH in information set H, with H equal to 1, 2, and so on. So UH, the action, is a function of the information set in which you are. This creates a number of pure strategies, and the mixed strategy is just randomization over this set of strategies. So with probability yi, player one will play the strategy gamma I, which is a map from information sets to actions. Now, if you're okay with this technical definition, then everything that we've seen until now actually holds exactly the same. Not only the specific results, like the very basic fundamental results, like the existence of Nash equilibria, but also the computational methods that we have seen, the properties for special classes of games, zero-sum games, potential games, everything. Okay, just replace these definitions for pure strategies and for mixed strategies in the picture. And here, this is just a bit of a schematic representation. What I mean here is that pure strategies are a subset of mixed strategies. Of course, that's where randomization is trivial. You pick one of the pure strategies instead of mixing them. And with the points here, what I mean is that there might be different Nash equilibria, but the circle dot means that you're guaranteed that there exists a mixed one, like by Nash existence theorem. So that's the one diagram summary of what we've seen in the first basic definitions. Okay, so just to make sure we are extending and we're not missing anything in the way, simultaneous play, which is what we've seen until now, can be represented as an inextensive form. So the matrix that we used to see before, right, when you have two actions for player one, north and south, two actions for player two, east or west, can also be in a simultaneous play, so they have to make the decision at the same time, can also be represented as a tree, where player one picks first and decides first, player two decides second, but player two doesn't know whether player one has picked north or south. So for all purposes, this is the same as a simultaneous play. Okay, so the extensive form is a larger set of games in matrix form, right, or in the static games. In this case, the information sets are 2, and the actions available at the first information set are north and south, and the actions available in the second information set are east and west. And so what you would write here, all the pure strategies are actually maps, you see, from information sets to action. It's just trivial because there's only one information set for action. Now, in the case of sequential play, which is the most natural first step towards multi-stage games, player one decides first and player two is allowed to respond. By that, I mean that the information sets are singletons. And by being singleton, that means that player two knows the decision of player one. Now, the information set for player two are actually 2 of them. By the way, they have different action spaces for the 2 of them. And what's interesting is that the pure strategies are actually all the possible maps from these information sets to the available actions. So you have 4 of them, right? You have a pure strategy, for example, where player 2 plays east in the information set 1 and plays up in the information set 2, and all possible combinations. But this matrix expression here, matrix representation here, is exactly equivalent to the tree representation, and you can solve it exactly as we solved the matrix games before. In fact, the first computational methods I'm going to present for multi-stage games is that you can convert a game in a static form as a static game, a matrix. You forget about all the tree and the order of choices. You just have an equivalent matrix representation, and then you solve the static game to find the Nash equilibria. Well, the main drawback of this one, which makes it almost always intractable, is that the problem size is exponential in the number of information sets. You saw it here, right? This means that once I start writing this matrix, even if this matrix is only useful to store the game and to be able to find an equilibrium in this matrix may be actually intractable quite soon if the game is big. Okay? And we'll see in the next slides that there are better computational tools if we add a little bit of assumptions to these multi-stage games. The one assumption which is key in making games in multi-stage games tractable is the definition of feedback games. So information sets in general can be really exotic, like they can represent players that don't even remember what happened in the previous stage and so on, right? But in many applications, I would say engineering application in general, but for sure the applications that we're considering today, players have recall of the past, okay? What does it mean? It means that in games with perfect recall, called also feedback games, no information set spans over multiple stages, and each subtree in each stage is not connected to other subtrees by any information set. Now, what you see down here is 3 possible examples. Only the one on the right is a feedback game, but let me give you an interpretation of why this is perfect recall or memory about the past. So you see here, the first example, the fact that player 2 nodes at this stage are joined in the same information set with a player 2 node on another stage, it means that in this game, player 2 doesn't remember, not only doesn't remember his own decision at the previous, the decision made, I don't know, by player 1 at the beginning, but he even doesn't remember that he had to make a decision at some point. Okay, so it might be the case in some games, but not in many games. In this other example, all the nodes of player 2 at the second stage are joined together, which means not only that player 2 doesn't know what player 1 has played, which is possible, but he doesn't remember what player 2 himself has played in the previous stage. Otherwise, he would be able to tell whether he's in this part of the tree or in this part of the tree. In a feedback game, you don't have these exotic things. Okay, feedback games there's one reason why they're particularly nice and good for the application that we were considering, is that you can define what are called behavioral strategies. Behavioral strategies can be defined in general. Behavioral strategies are maps that assign a probability distribution over the action to each information set. So notice the difference. In pure strategy, you have a map from information sets to actions. In mixed strategy, you mix the pure strategies. In behavioral strategies, you have a map, as in pure strategies, from information sets to small vector where you randomize over the actions available at that information set. They are not the same thing as mixed strategies. You can actually prove what is represented here. You can prove that behavioral strategies are, for feedback games, a subset of the mixed strategies. But you can also prove that it's not restrictive to consider only behavioral strategies, in the sense that you are not interested in any Nash equilibrium which is not a behavioral strategy. First of all, because you are guaranteed that a Nash equilibrium exists in behavioral strategies, and that's usually all you need. And second, because any other Nash equilibrium outside of the mixed strategy is going to be equivalent to some other Nash equilibrium in the behavioral strategies. So the details of this one are what are contained in Kuhn's theorem in the monograph that we're going to post online. But the take-home message here is that if you have a feedback game, you can randomize at the level of the individual information set. You don't need to look into this huge set of mixed strategies. This is very good news. The behavioral strategies is a set which is computationally very tractable. Backward induction works, and that's what we're going to see in the next couple of slides. But in general, if you want to have a feeling of why it works, of why it's a good idea to work in behavioral strategies, the behavioral strategy is a space of dimension much, much lower than the space of mixed strategies. Okay? And we will see in the next slide, backward induction returns also a subgame perfect strategy, which we're going to define in a second. So this is just a preview. Okay, so from now on, randomization for multi-stage games, it's a randomization that you can do information set per information set. which means that once I travel I play the game, when it's a player decision to make the next action, the player can randomize and decide how to proceed. And then it will enter in another information set, and then another randomization is going to happen. This is in contrast with mixed strategies when the randomization happens at the very beginning and then they commit to a pure strategy. Okay. So what is the backward induction procedure that I promised in the previous slide? Well, imagine that you have a game with capital K stages, and it's a feedback game. So because it's a feedback game, I can take the last stage, stage K, and I can look at all the little subtrees that constitute stage K. Now, I'm not drawing information sets in here, but you can take, because it's a feedback game, you know that each of these subtree will have its own information structure, but will be separate from other subtrees. So these are a large number of small one-stage games at the last stage. And so you can solve them with the methods that we have seen before. So you can find a gamma K, capital K star, and a sigma capital K star, which are the Nash equilibria strategy for the subgames at the stage K. So these are going to be different for every subgame, right? You have one per each. They are just separate games that you can solve. And for each of them, you will have a value. Now, it can be a value per player if it's a non-zero sum, or a value for both if it's a zero-sum game. Now what you can do, you can just prune the tree, remove the last stage, and attach the value of these subgames to the roots of the subgames. No, there were all these games here. And now we just attach the value E, F, G, H. Now these are a large number, but increasingly smaller number of individual games. What does it mean to solve this subgame here? It means that I'm finding a best strategy for stage K-1. It's a Nash equilibrium. And this is assuming that, of course, from now on, I'm going to play optimally. But you're going to solve it independently for all possible subgames at the stage K-1. So this gives you, when you complete it to the root, gives you a subgame perfect Nash equilibrium. A subgame perfect Nash equilibrium is exactly the kind of solution that we've just constructed. It's a Nash equilibrium behavior at every stage, regardless of what happened in the past, because I'm solving each of them separately, and assuming that Nash equilibrium strategy is going to be played in the future, because we have replaced the leaves of each subgame with the value of the subgame rooted in that leaf. Okay. This is where the robustness of subgame perfect Nash equilibria come from. The fact that I know everywhere in this game what's the Nash equilibrium or the best thing, let's say, for players to do, regardless of what happened before, even if I end up in a place where I shouldn't be. Okay, and that's the first method, and which in general you can do, right? If you have a feedback game, you can apply this method and solve the game. I'm going to show you with a toy example what's usually the problem with that method. Although this works for many applications, right? But what's usually the method, the problem? So consider this variation of the game that we had before, right? It's exactly as before. The player one needs to reach the safe zone and can go to the left, to the middle, to the right in this path, in this channel. At every stage, when player one decides where to go, player two can decide which row to block. Okay? So it's a sequence of simultaneous decisions, but the more you progress to safety, the more player one has a probability to actually reach destination in one piece. Now, imagine that we draw a tree like this one for this game. How many small subtrees do we have to solve? Well, we only have 3 finite actions per stage, but we have a large number of stages. That means that when I take the first stage, I already have 3 times 3. I have 9 possible initial points for the second stage. At the second stage, I have 9 times 9, right? Because remember, the tree represents all the sequence of decisions of all players. Now, if you wanted to solve this game, what you have to solve is something of the order of 3 to the power of 20, linear programs. I mean, you are lucky that this is a zero-sum game, so at least it's a linear program and nothing worse than that, but it's a lot of them. And of course, the key observation here is that if you are at stage, I don't know, 3, in any given position here, the probability of escaping, and in general, the rest of the game, the remaining part of the game, does not really depend on what happened before, right? So suppose that I'm here, player 1 is down here, player 2 has blocked the middle row, so it didn't block the player 1. Now we start playing from here. Does it really matter what happened before? No, player 1 is alive and player 2 is still trying to catch it. And so the solution, the optimal strategy, and the value, the probability of escaping from now on are simply given by a much simpler piece of information. Your position up or left, middle, or right, okay? And that's the key point that you probably will come natural to you if you try to solve this game. The backward induction can be done on the position, on a state of the game, instead of the game tree. So you would have to solve how many of these, like 3 times 20 linear programs instead of billion. Okay. And that's exactly what, as you can see here, the game becomes even larger if you have multiple actions. So this idea of relying on a state of the game instead of relying on all the past decision is particularly powerful when agents have a lot of actions available, or even a continuous set of actions available to them to decide. So for example, in here, we consider a feedback game in extensive form, like the multi-stage games we are looking at, where player 1 action, player 2 actions are 2 vectors, right? Their decisions are vectors in Rm and Rn. Now, if you have these 2 assumptions, assumption 1, there is a state that evolves at every stage, xk plus 1, function of the previous state of the game at stage k, input u for player 1, input v for player k. And you have stage additive outcome. So the outcome at the end of the leaves is going to be a sum of functions evaluated over the states, over along the stages of the game. Then at each stage, the state is a sufficient representation of the game for all purposes, right? So you can do the backward induction on the state instead of keeping track of all the past decisions. Just as a recap, we need it to be a feedback game. There needs to be a state and stage additive outcome. But it's really common in when the state represents positions, velocities, in things that are really close to us. The representation is also slightly different in this case, right? So now this is a representation much closer to control theory, right, than to game theory. You have a state. You have the next state, x2, which is a function of x1, u1, and v1. And these u1 and v1 are function of the state before. So multi-stage game really looks like a discrete time system. Remember, strategies in game theory were maps from information sets to actions. That's why here they are feedback laws, maps from states to inputs. And in this example, players have the same information available. You see both player 1 and player 2 implement a state feedback from x1. But this is, there are variations of this. You could have player 2 maybe knows the state with some delay and so on. You're allowed a little bit of variations in that case. And now let's do the final step to make this control theory instead of game theory. Y representing x1, x2, x3 in this way. Let's just loop it around. Okay. Still, this is a game. Okay, so what's the computational method that I'm suggesting here? Well, it's simply to do backward induction on the state instead of the game tree. So how does it look like? You initialize at the very end of the game the value of the game to 0. So you have a function which is function of the state after stage k. Okay. Then you look at stage capital K and you determine two functions, gamma k and sigma k star. These are not numbers, these are functions of xk that satisfy this Nash equilibrium condition. This is exactly what we've seen before, but we are using the fact that the stage cost is additive. So the gamma k star function of xk, it needs to be the best that player one can do to minimize the stage cost. This is the cost at the last stage. And the next stage. The next stage is going to be a value function not in the current state, but in the states where I xk plus 1, which using the updates equation is function of the current state and the inputs. Again, this is a best response kind of condition. This gamma star is optimal when player 2 plays sigma star. Sigma star is optimal when player 1 plays gamma star. What I've done here is exactly what we did here, to go from this one to this one. Okay, but now it's a function of the state instead of being function of the subgame where you are. We are doing a backward induction on the state and not on the game tree. Notice that the decision, both player 1 decision and player 2 decision, enter in two places, both in the stage cost, but also in the future cost given through the update equation for the state. And now once you do that, then you solve, imagine you can solve this one. Then you have the two values now for capital K and not K plus 1 anymore. These are the value of the subgames rooted in xk. And then if the game is still, if the tree is still not a one-stage game, you go, you prune the last stage and you go back to step 1 and you continue. So if you've seen dynamic programming and optimal control, that's really the same thing with value function and so, but the usual Bellman equation when you have this kind of optimality is replaced by a Nash equilibrium condition. One is the best response to the other. Okay. Now the bad news about this, the closed form solution for this kind of Nash equilibrium condition, in the same way in which in optimal control you can do maths beyond linear quadratic regulators, it's also only available for very special cases. For example, for multi-agent linear quadratic regulators. Okay? So if you want an exact solution, then you need to restrict to a very few exceptions. One of them is multi-agent linear quadratic regulators, where the state update is linear. Okay, that's fine, like kinematic equations. The cost is quadratic. For example, speed, position tracking, the distance from the reference points. And then in this case, you can build an explicit Nash equilibrium controller. The procedure is very similar. It's in the monograph. It's very similar to what you would do in single agent LQR or optimal control. You have a quadratic value function. You claim that the value function is quadratic, and then you recursively prove that this is true. What you get is a two-coupled Riccati equation, and you get a linear feedback control. This might be enough in some situations. So for example, we have an example with the track platooning where different tracks owned by different people, they want to minimize their fuel cost and they want to track their distance from the one above and the one before, right? If it's not the same owner for all the tracks, they have their own individual fuel costs, then they should solve a multi-agent LQR problem instead of an LQR problem, a standard LQR problem. But it's almost only the only application where you can actually solve this coupled equation in closed form. Now, what do you do we can, by the way, we can have a look if you're interested of how does the derivation look like, some backup slides if you want. How does the open loop Nash equilibrium strategy work? So what do you do in general? Well, in general, you cannot solve this problem in one shot. What's much more tractable is to find all the possible future inputs, right, in a trajectory, in a I can say in a multi-stage game, right, for the next stages, that minimize the outcome for player one when player two is playing their optimal strategy VK star. Subject, of course, to the updates, right? So the updates give the same link as before, where the next xk plus 1 depends on xk, uk, and vk star. For the second player would have to compute the entire trajectory from now to the final stage that minimizes the cost of over the entire multi-stage game, given that player one is playing uk star, subject to the same equation as before. Now, what may be not apparent from the mathematical notation, but it's very important, is that this problem and this problem are quite different, because these were functions of the state at every stage. This is a sequence of vectors, right? Of real numbers or small vectors. Okay. This is only optimal for a specific VK star, not for a function of VK star, function of XK. Okay. Which means that if I change U, which changes my cost everywhere, I change X, I don't change VK. The V is constant and is this V star. So what you get as a result is that the two players will be able to compute two sequences of inputs, and then they have to commit to those and apply them no matter what. Now, is this a tractable problem? Well, it's still a complicated problem, but it's an optimization problem. It's just an optimization problem where you have two minimization at the same time, and it's coupled through the fact that they have the same update here, right? The V and the U appear in both in a cross-term kind of fashion, but you can solve most of these problems. Usually, you force some local optimality condition. Most of these problems are not convex to begin with, so you can apply some local optimality condition in the form of variational inequalities, something like you find a U star and V star that in the unconstrained case, they zero some gradients at the point U star, V star. In the constrained case, you would have some variational inequality, like the projected gradient is pointing towards the set of feasible directions. Or if you dualize some of these constraints, and I think we're going to look into something like this in the talks in a little bit, what you get is a set of KKT conditions, right? So conditions of both the multipliers and the primal variables. There's not much to add here. This one you can solve, but you get an open loop trajectory. So if you remember at the very beginning, we were saying that an important thing of why you want to do backward induction is the robustness, right? We're saying here that the robustness of having a solution which is valid regardless of what happened in the past. Well, this is not true if you do this open loop construction, right? In this case, in the closed loop, it's a function that you can evaluate in every stage where you are. In the open loop, it's a function, it's a sequence of inputs that you apply no matter where you are in the tree. Now, the connection between the two, that's it's typically used, and it's not only in the game theoretic setting, but also in typical control problems, is to make this approach a receding horizon open loop approach. So what you do is that if you end up in a point which is not the one you were expecting, then you resolve a new game rooted in the current node. So this gives you back a bit of the robustness of the closed loop Nash equilibrium. The main drawbacks of this kind of approach is that computationally you're not solving it offline. You need to be able to resolve the game, the new game, in every once the new state is disclosed to you. So the two different players or a centralized coordinator would actually have to know the new state and solve, throw away everything they've computed because it was for a different trajectory and solve a new Nash equilibrium trajectory for there. Okay. It's still much better than solving the entire game tree. It comes with a cost of a real-time optimization. Okay, so with this one, I've covered what I want to cover for multi-stage games, including closed loop and open loop Nash equilibrium, which is the last thing. There are a couple of things that I would like to mention before opening the floor for some questions. There are clearly things that we have not covered and which are still relevant for the topics that we are considering in this tutorial. I wanted to mention two of them at least. One is Bayesian games. Bayesian games are games where there's something about the other players that you don't know. This is typically called the agent's type, theta here, right? So for example, the cost function for player one and player two depends, the outcome depends of course on the actions of player one and the actions of player two, but also of some parameter theta one and theta two, which are not known to the other. So in this case, it's a game with partial information. Usually, technically, from a technical point of view, you can convert these games into non-feedback games where there is an additional player nature. Okay, so if you're looking for a way to solve this problem or to prove something, typically it's enough to say it's a usual multi-stage game, but the very first action at the very beginning of the game is played by a third player, which is called nature, which decides theta one and theta two. Okay, maybe based on some distribution that you know or so on. So from a technical perspective, you can convert them, massage them back into the formulation that we have seen, although what you get is a non-feedback game. From an interpretation point of view, there is something to be said that we're not going to cover here, but the agent's decision now is not only their strategy, it's also their belief about theta one and theta two. So when progressing through the game, they have to update their own strategy. They also have to update their belief about what is theta of the other player. And typically this happens through like a Bayesian update of that. That's why Bayesian games. The second thing that I think could be relevant for these applications, but we have not covered in this to our tutorial, are Stackelberg games. Stackelberg games, we have actually seen one of them, was the one, what's this one, right? It's a game where one of the player plays first and the other, the one responds. So they're typically called leader and follower. This is an asymmetric game compared to the simultaneous play, right? One of the two plays first and the other one plays second. It requires some special care if you want to study them. For example, the concept of non-credible threats, like what happens if player two has a strategy, but then it's clear to both players that player two would actually not stick to the strategy committed to if player one makes a certain decision. You can create these strange constructions. But the good thing is that this is computationally tractable under some assumptions. As I mentioned at the beginning, there's a class of games, for example, security games, which is games where the leader decides which targets he wants to protect and how to use resources, and player two has to respond based on that. So something very similar to this escape game that I was presenting, but not in a zero-sum fashion, like you have a different cost depending on what targets you want to protect. And these are Stackelberg games that can be studied very efficiently. And they're actually one of the latest success stories of game theory in terms of recent applications, at least in the last 10, 20 years. Okay, and finally, a couple of things that we haven't covered are differential games, which are games where the update for the state X is given by a node E and not a discrete time update. It's a very elegant formulation. A lot of the things translate to that, but then at some point you need to go back to discrete or at least a hybrid form when agents need to make a decision if agents are actually autonomous vehicles receiving information, doing computation, and actuating their vehicle. And population games, which are a class of games where the number of players is large enough that you can actually simplify the problem to a point that you can achieve some results that are not trivial in regular games. They become particularly tractable because of the large number of agents involved. Okay, I'm actually happy to conclude a couple of minutes earlier. Maybe I can address some questions and see what's your points on what I presented. Thank you for staying with me.
All right, thank you, Saverio. So there are 3 questions. So the first one is non-technical, but someone got fascinated by the way you're making the presentation interactive.
Okay.
So he or she is asking, what kind of tool are you using?
Okay, I can share that, but it's impressive. The name is quite generic, so you won't be able to find it by Googling it. But if you Google impressive PDF presentation, then you get it. It's a very rudimental tool, but it does what it promises. Yeah, something like that.
Okay, then the second one. How is the loop model different from an MDP, besides having multiple agents?
It is basically that. There is one thing that I haven't covered here, and in fact, you can see it when I say that strategies are maps and they become feedback laws. Well, strategies could be also random. So you actually could have a random element in these decisions, and you could also have a random progressions of the state if you wanted, right? This would make it even closer to MDPs. At the end, it's basically what it is, sure. And the fact that you have, of course, I mean, as you were mentioning, you have multiple competing agents instead of having typically a policy that you have to compute or something.
Okay, I think the last question you partially answered already after it was asked, but I'll repeat it. So is there an example application paper for the open loop Nash equilibrium strategy?
So plenty, actually, in the sense that usually the closed loop Nash equilibrium is something very complicated to study. But if you mean open loop instead of receding horizon, it really depends, in the sense that it's very natural if you can compute an open loop Nash equilibrium to also reset the game in case, periodically, once you have new information. Whether you can really apply an open loop Nash equilibrium trajectory, it depends a bit on the rules of the game. Like, are agents really committing to a trajectory? Like, you can imagine, right, a protocol where agents need to agree on a trajectory, and then they commit to that. I mean, they're not allowed to depart from that trajectory once they have announced it. But the step from open loop to receding horizon, it's a very natural one. Once you have new information, you can solve a new game, which is basically this one. But if the difference is between open loop and closed loop, then open loop is typically the thing that you typically see, because solving the closed loop, it's almost reset for multi-agent LQR, unless you go into some approximate dynamic programming kind of approach. But as an exact solution, it's really limited to a few cases. Let me add, I'm just looking at the questions here. Let me add something to the second question about MDPs. One thing that we are also assuming here is that, which is not necessary, but we have it, at least in the way I've presented it, is that these games end. So there are also games where you're really in an MDP, in the sense that it's also like there could be cycles, right? You could be replaying the game, forever until you get into a sync or something, right? I don't have it here because they require something slightly different. I mean, there's no last stage K to solve, right? So that could be like maybe the closest to this one is an MDP with an acyclic graph or something like that, right? If I'm explaining myself.
Yes, thank you. I think it was clear. So unless there's any other question, I think we can stop here.
There is one comment by Alex that I mean, he can also say it himself, but I think it's very much on point. Is that once you solve a receding horizon games, it's not as simple as I've presented here, in the sense that even, I don't know, recursive feasibility of the problem. I mean, you typically have similar issues to the one that you see in model predictive control. In model predictive control, you might have to set terminal constraints to get stability. You might have to make sure there is recursive feasibility of the problem, and so on. You actually you face something similar, or the similar problems in here. Maybe Alex is going to touch on these points in this presentation as well.
No, unfortunately, I don't have the time to talk about it, but or at least not for the game part. But yeah, the issue is really, I mean, if you play it in a recursive fashion, it's possible that you cannot guarantee that at the next time step, for example, you can avoid collision, even though your plan was collision free. And yeah, this is kind of, I mean, especially once you get, I mean, this is an issue I even run to in simulation where things are nearly perfect. So yeah, it opens a very interesting kind of work, but it's also extremely complicated to solve it, or especially on, you know, less the theory is maybe clearer than the practical implementation.
As often. Thanks, Alex. Okay, so Alessandro, if you don't see any other questions, then we can, should we move to Gather Town and take a virtual coffee before we start with the presentations?
I think we can take a virtual coffee, and then we'll see you back here at well, 6. Well, it's 4 UTC with Alex's presentation.
Okay, see you back then here. Bye.
Bye-bye.